All right, stat students. So we got a video today to sort of finish off the practice that you're going to be seeing and the assignments that are due. Just sort of one last final push here. We have our test coming up next week. So let's go ahead and get into this video. All right, so we did a similar problem to what I have up here the other day. So I've underlined the means for these different distributions. This is from that same context, the Gettysburg Address. Okay, and we have 4 different symbols for means, and I've shown those right here. And we have to be able to identify which symbol goes with which. Okay, which goes with which here. All right. So just like the last video, I'm going to pause this, and you guys are going to, I'll say 1, it'll be multiple choice A, B, C, D, 2 A, B, C, D, and 3 A, B, C, D, and you have to figure out which one goes with which. So I'm going to go ahead and pause and give you all a chance to work these problems. So go ahead and do that. Okay, so let's talk about this. First off, this first distribution is the population data. So the symbol that we use for population mean is going to be this one. This is mu, and it represents population mean. So the mean, this was the word links of the Gettysburg Address. Mu is the mean word length of all of those words. It's the population mean, okay? Next, B, X bar. This is like the first symbol that we ever saw when we are calculating mean early on in the year. Describes the mean of samples, okay? So this 3.8 was the last sample I took. So 3.8 matches to that, okay? Next, C goes with the last one, okay? This is the mean of the sampling distribution. So this is important here. This means of the sampling distribution of X bar, okay? So this is the mean of sample means. And you'll notice that this number here is very close to this, and that these symbols here should always be equal, okay? Those are always equal based on our rule that we wrote down all of our rules the other day. So I've nicely typed these up like this for our reference today, but all of our rules should be or that rule follows here, okay? For proportions, it was this. So why do we not have this symbol here? This one is not a part of this, okay? Well, because we don't have any proportions happening. We talked about that in the last example with the standard deviations, which is over here, right? We could not use this symbol because there were no proportions involved, okay? So that's why those are the answers for this, okay? So what we're going to talk about today is we're going to look at the newest sheet, and this is the final worksheet that's due. This is going to be due on the, let's pull up the calendar, the 16th is when this is due. You have 2 assignments that are due on today, which is the 12th for when this video is made. So you have the Delta Math assignment, which is the problem set, and then you also have the the other worksheet that we looked at. Let me pull that up. That's this one here, and it has all of these problems on it. And here are all the symbols. You'll notice that we pretty much talked about all of these symbols just in those 2 examples. Most of them are here. So you're gonna, here was something that somebody said. They said, okay, be able to name them. Well, they're like, okay, well, can I just say that, oh, this is mu? Well, no. Like, for instance, this is not acceptable for you to do where you're writing the word mu. I don't care about that, okay? What you would want to write for this one is population mean. I want you to describe what it is. We knew that this is the mean of the population. So make sure that you write out the word population mean. This one was population standard deviation. Sample mean, sample standard deviation. And we're just writing out what those are because on your test next week, which will be supposedly on Wednesday, we're going to see what the snow does. You're going to have to match up the symbols to their correct word. Okay. So make sure that you are working on this one. This is one that is due tonight. I believe that we practiced. Well, actually, we didn't practice any. That was what our last lesson was about. Was looking at some example problems to practice for this, for questions 10 through 13, and then you have all the common questions. A lot of people have been asking about what this wants. So for this situation here, I just want to talk about this. This needs you to identify the statistic and the parameter. You have bold-faced numbers here in each setting. One of these is a statistic, one of them is a parameter, okay? Remember that parameters describe the population, statistics describe the sample. It says use appropriate notation. So what we want with that is this. And I will be fine if this is how you write it on your sheet. Since this is a situation of means, we know that one of these is going to be mu, and one of them will be x bar. The statistic would be the x bar, the mu would be the parameter, right? One of these is the population mean, one of them is the sample mean. So that's what you're having to do on this one. And I just wanted to be clear what that meant by appropriate notation. And I'm okay, like you don't have to say, like write it exactly like this, parameter statistic. If you write this, that's enough for me. If you're writing the symbols, the appropriate notation implies that you know what it is, parameter or statistic, based on if it's describing the sample, that'd be sample mean, or population mean, okay? All right, so there's that sheet. Now, I want to talk about this worksheet here. Zoom in. This is the brand new one. This one is due on the 16th. Okay, so you have some time for this one, so I would focus on the other ones first, but I do want to talk about this first problem here, okay? So if you're able to print out this worksheet, that would be ideal for writing. Obviously, you can write it in your notes, but we are going to be working this question right here, number 1, okay? So let's, I've got a PowerPoint slide that I'm going to be writing on. I want to make this all, hold on. I'm going to make all of this bold just so it's easier to see. That seems fine. Okay, so let's talk about this. And hold on, I gotta get one more thing set up. Okay, got it. Let's go. So it says taxi fares are normally distributed with a mean fare of $22.27 and a standard deviation of $2.20. Okay. So we start with part A. It says which should have the greater probability of falling between $21 and $24, the mean of a random sample of 10 taxi fares, or the amount of a single random taxi fare, okay? So as soon as, we talked about this last time, as soon as you see the word probability, we know that we have to do a normal CDF, okay? That should be like the first indicator here. And we're going to be doing a norm CDF of draw. We have a sample of size 10, so we have n equals 10. And then we have single, which is n equals 1. Okay? So before we're able to do this calculation, which we're going to need our calculators, so you can go ahead and have that handy. We'll start booting mine up. We have to make sure that this distribution that's going to be created from these samples, the sampling distribution from the population, will be normal. Okay? So how do we determine if this is going to be normal? Well, first off, we have to decide, is this a situation of X bar or P hat? Okay? So we have our, remember, because that's what we're going to be using for these rules that are on the screen right now. You have to first identify what is the situation. So I'm going to pause the video and you're going to answer one or the other situations. Is this a scenario of X bar or is this a scenario of P hat? All right, so you had a chance to answer. It was 50-50, right? But hopefully you knew what it was. This is X bar because we see the word mean We also see the word standard deviation. We wouldn't see that word standard deviation if it were in a situation for proportions. You see the word mean again here. So yeah, those are the key terms that are telling us that, right? So this is x bar. So how do we prove normality for x bar? Well, we have n is, oh, I have that backwards. Hold on, let me edit that. Equation n is greater than or equal to 30. Is that our case? Well, look at our n's. No, they are n equals 10 and n equals 1. So right now it doesn't seem like these distributions are going to be normal. The other rule is that the population is stated as approximately normal. So we go back to our descriptor of this population. Taxi fares are, oh, there it is right there, normally distributed. So we'll draw a line under this. That means we're good to go when we say, okay, can we run these normal CDF calculations? Yeah, we can, okay? So that's one of the first checks you always want to do. I know it's the third rule, but if you do the checks for normal and they don't work, then you get to skip the question. You don't have to do any of the work. For AP students, this is something like on a free response that needs to be shown, okay? Has to be shown that you're going through the process of checking this, and you definitely don't want to miss a question because you didn't do the check, but you showed the calculations, okay? All right, next. So we have lower, upper, mean, and standard deviation for each of these. Okay, so we're gonna write these down. You should be writing them with me: upper, mean, and standard deviation. Okay, so we know that we want it to be between $21 and $24. So which one is going to have the higher probability? A sample of 10 or a sample of 1? Now you may already have some predictions going for this. I'm not really sure where you're at with understanding how these probabilities work. I had just a few people like in person that were able to sort of see what was happening with this, but I've got a good visualization for you today that we're going to look at. But we know that our lower boundary is $21, upper boundary is 24. So we're going to put that for both. Okay. Now, what are the means of these distributions going to be? So mu of x bar, right, for each of them. Mu of x bar. What is that going to be? Well, we have our rule for that. It's this top one right here, right? It's always going to be equal to the population mean. Well, this right here, this 22, 27, just like we did for the bell work, we're able to identify that as the population mean. This is mu, right? It's describing the population of taxi fares. So we know that it has to be equal to 22.27, and that goes for both of them. So I'm not even going to write it here. I'm just going to put it here, 22.27. Put that in for both. Okay. So we have that. Now, what about the standard deviation? Because that's what we also have to have for this. Well, we have to use this formula here, sigma over square root n. So we're going to put that sigma over square root n. That goes for both of them. So what is sigma? Well, we identify this right here as the standard deviation of the population. So that's sigma. So this is 220 over square root of n, which is 10. Get rid of this. Now, we are not allowed to do this if this condition here is not met. If this condition here is not met, then we're not allowed to do this. So let's actually check that first. Is the sample of size 10 less than or equal to, is 10 less than or equal to 1/10 of big N? Well, big N is all taxi fares ever. So yeah, that's going to be a lot of taxi fares. And at this point, that's really all we need to do is sort of think through it. Now, if they give us a solid number of the population, then we'll want to put that in there to check it. And remember, if this doesn't work, then we can't do our calculations either. So that one actually does work. So we can calculate this. Let's go ahead and what is happening? Okay, that's good. So we can actually go ahead and do this calculation. So we do make a fraction, control divide. We want 220 on top. And we want to divide that by square root of 10. So 0.6957. Okay, so that's our standard deviation. So we have what we need for our calculations. We can type this in a normal CDF. Let's do the next one though, and so we can do a good comparison. So we get 220 over, and by the way, since 1 is smaller than 10, it's also going to pass that 10% condition. I want to type that in actually. Hold on. 10%. That's what that rule is. Okay, 10% condition. That shows independence. Don't forget that, right? Okay, so now let's continue with this. We want square root, and you'll notice with 1, actually the standard deviation is just going to stay the same. All right, so the same question is asked. Which should have the greater probability? Okay, we have two two probabilities. I cannot circle that. Anyway, we have two distributions here. Which one's going to have the greater probability of being between 21 and 24? So maybe you can answer this now just by thinking about it. The only difference is the standard deviations, right? Okay. We're really asking what is going to have a higher probability, the standard deviations of 21 to 24 between 21 and 24 with a standard deviation of 2.2 or 0.695, okay? Well, to help visualize this, we know that standard deviation is the spread of data, right? So which one is more spread out? Well, the higher standard deviation, okay? And since the mean is 22.27, think about this. If I go plus or minus this standard deviation here, that's 20 to 24.4. So already in one deviation, you've already passed your limit there. And how much data falls within one deviation? That's an old rule back in the first couple units, or it's in the third unit that we did. Well, we have that 68, 95, 99.7 rule for normal distributions. Well, 68% of the data falls within one deviation. So think about this one. If I add or subtract, this one isn't going to have, the deviations don't go towards these boundaries. It's going to take several boundaries to get there. I think like 3 or 4 to get there, okay? So with that in mind, you might have a better answer as to what would have the higher probability, but let's get a better visualization, okay? This is Desmos. I'm actually going to copy and paste this calculator into, I'm going to put it here just so that I'll save it for later so that you guys maybe can go in there and play with it. And see if, because you can use this calculator that I have to answer the questions, okay? And we're actually going to do that. So we have a normal distribution. This one here is called a standard normal distribution because the mean is 0, standard deviation is 1. So what we want to do is we want to put in our mean. So we have the 22.27, and then our standard deviation of the first one is 0.6957. If that's right, let's double check. Yes, okay. So you'll notice that it's gone off the screen, and what's happened is it's transformed, right? We went from a mean of 0 to a mean of 22.7, so it shifted to the right, 22.7. Okay, then we changed the standard deviation from 1 to 0.69, so it got smaller. Okay, so we're actually going to zoom in on this distribution. You'll notice it looks just like what it was. Okay, but it's always, the way they have this set up in Desmos, it's always going to, if I zoom in on it, it's going to scale appropriately. Now I could zoom out. We see it there. It looks far away, or I could zoom in, whatever I want to do, but as long as I hit this button here, it'll go back to normal. Okay, then we can find the probabilities. Okay, I want to find the probability between that it's going to, how many percent of the data, what percent of the data is going to be between 21 and 24, and you can see there's the shaded region. Okay, that's a lot of that distribution right there from 21 to 24. So let's compare that to, let me copy this. Okay, compare. I'm not going to draw it until after I put in standard deviation. So our standard deviation is 2.20. So we expect this to be more spread out. Okay, it should have the same mean but more spread out. So let's look at that. That distribution, it doesn't even look normal, right? But if I zoom in on it, there it is, right? And it's gonna go between the same boundaries here and here, okay, or 21 to 24. So let's do that. Find cumulative probability 21, 24, and you can see that blue distribution, the one with less spread, has more values that are closer to that within that deviation. Look at the difference in the probabilities. This is 96% essentially, and this is 50%. And I can actually zoom in to either one of these and compare the size of the area. So I think this is a really good visualization for how these distributions are working. Again, you can feel free to get in here and play around with some of these. You can do all of your calculations like this, but what I'm going to do is I'm going to copy in the answer here. Okay. So this is our answer for that normal distribution. Okay, that's our answer for that one. Then we grab this one here. That in there. Okay, so there's our calculation. Draw, please. There we go. So this one is larger. And why is that? Well, it's because, so if you're saying why here, especially AP students, why is this happening? Well, because the standard deviation is less, more values will be centered around the mean, okay? A higher percent, and we're seeing that as it relates to area under these curves, okay? So if you want to try this on your own, typing this in, if you want to add another one, you can just hit Control C or just copy. I wonder if that, yeah, will it let you copy? It won't. So Control C and then Control V. I think if you're using a MacBook, it's Command C and Command V for Macs. Not sure about Chromebooks, but yeah, you can sit in here and you can play and compare these distributions that have the same means. Pretty cool way of visualizing a normal distribution, okay? So what about the bottom part here? Which should have a greater probability of being over 24? Okay, so greater than 24, so from 24 to infinity. Which one is more likely? Well, we're going to use, everything is the same except the boundaries. So you're just moving these shaded regions. So which ones have more data greater than 24? Well, let me hide this for a second, and we're going to change this to 24. And how you get infinity on here, if you're going to use this to help you with some problems, you type infinity, you type the word, and it'll give it to you. And look at that. A small portion of this graph, because of the small deviation, the small amount of deviation, is going to be shaded. That's a tiny amount. Look at that. Less than, it's 0.6%, right? So it's a tiny percentage. We compare that to the larger spread, right? So let's do that. That's we want infinity. And we get 22%. So let's look at this. Look at that comparison there. It's just more spread out. So you have more of a chance for the values of these taxi fares. Like any outliers, they have a more probability of being larger because you're taking one sample. So it can be very variable, okay? But when you have samples of size 10, it's more likely that they're going to be closer to the true mean. So there's the idea. That's the concept here behind this, okay? So when we answer this question down here, we have our probabilities. We're just going to answer the question. We're going to say a single randomly selected taxi fare because the values of a single random taxi are more likely to be over $24, further away from the mean due to the spread. So because the standard deviation is larger, so you can write this, because the standard deviation is larger, more values will be over $24 for a single taxi. Okay, so that's why. All right, that is the majority of what I wanted to cover in this video. I thought this video would be pretty longer, but it's doing pretty good here. So I'll stop it there. And if you have any questions as you're working today, reach out to me. I know in person we are just doing a work day, so I can answer questions if you have them. I might even talk to the class about them. If you want to send those, it might be helpful for everyone. So I'll stop it here. Good luck, and reach out to me if you have questions.